Welcome everyone to week 11 in review. Today we're going to cover the small gain theorem, which one way to think about this is a generalization of Nyquist stability, and in particular the stability margin. So if you recall what the stability margin is, it tells us that, so here's, it's best to illustrate this by an example. So suppose that we have our Nyquist diagram that looks like this, and -1 is out here, and this is oriented like this. So you'll notice that as long as the -1 stays outside, there are no encirclements of -1. However, if -1 were to go inside, then we would have 1 or possibly 2 encirclements. So the question for the stability margin is, what's the perturbation that's allowed in order to so that we can guarantee that we have no encirclements of -1. And the key on the graph is this minimum distance from the curve L of gamma to the point -1. So in the, Nyquist is in the context of the feedback unity loop, which looks like this. Sign. Now suppose that we have a perturbation in the plant. So P true is equal to P plus delta. What does that mean? That means that L true is equal to P true times K, which is equal to Pk plus K times delta. So this is equal to L plus K delta. Now, this line that I drew here, this line segment that represents the minimum distance from L of gamma to 1, this tells us that as long as L of I omega minus 1, or in other words, L of I omega plus 1, as long as this distance is always bigger than the magnitude of the perturbation, which is K delta, K of I omega delta times I omega, then we're safe. So let's rewrite this, and we see that this is the same as writing that P of I omega, K of I omega plus 1 divided by K of I omega must be bigger than delta of I omega. Another way to write this is that if I bring this all over onto this side, is that delta of I omega times K of I omega divided by P of I omega, K of I omega plus 1 has to be less than 1. So the reason I write it like this in this last form is that this is the form that we'll see in the small gain theorem. But I think this is a useful way to think about it. So let's see what the small gain theorem says, and then we're going to come back and apply it to the feedback unity loop and see that we get exactly this. So the small gain, the concept is the following. Let's model uncertainty by an unknown block in the block diagram with a delta inside. So for example, in this case where P true, in the case above where P true was equal to P plus delta, instead of P, we would model this in this way. And you can see that the effective transfer function from input to output of this particular block is indeed P plus delta. This this concept allows us to model many types of feedback. So for example, if instead of additive error you had multiplicative error, so if p true were equal to p times 1 plus delta, this makes a lot of sense because it's as though you have percentage error. Then the block p, we would modify this by something like this. Now why does this work? Note that what is the transfer function from input to output? Well, we have two things in series. This part is 1 plus delta, and then it's in series with p, so it's multiplying by it. And so indeed we have this is equal to p times 1 plus delta. And there's many other things that we can model, as we've seen in class. So for example, if p true were equal to p over 1 plus p times delta, then we would model this with feedback loop. And we need a minus sign here. Similarly, we could model if p true were equal to p over 1 minus p times delta, then we would just take away that minus sign if this is p. This models this transfer function. So the point is that there's a lot of flexibility in modeling with this block. So now the general concept is the following. Let's suppose that our original system, we're going to call it H here, has input to output is R to Y. And we're going to model this additional block. It comes out of somewhere. Notice that this is indeed the case in all of these above examples. And so what happened, this may have been attached to a feedback unity loop, let's say. In this case, what I'm circling now in red would be H. And here we've got our delta. Similarly, in this case, where in the picture it looks like feed forward, it doesn't matter. We've got our feedback unity loop that I'm drawing in red. And we've got our K somewhere here. And again, what I'm circling in red is H. And what we see, it doesn't matter the direction. The point is that we've got something coming out of H, going through delta, and then coming back into H. Okay, and so generically, we can capture all of the structure as depicted here. Whoops. Sorry about that. So let's label these additional two inputs and outputs. So let's label this input as phi, and this output as C. And an important initial assumption is that assume that we've chosen the controller so that the system is stable to begin with. Okay, it doesn't make sense to have an unstable system because if you have instability and then you're adding some perturbation, it doesn't make sense to hope that this perturbation that's not in your control will somehow stabilize it. So the starting assumption is that H is stable. And what I mean by H is stable is that if we were to cut delta out of the loop, forget about it for the time being, then the transfer function from R to Y, the transfer function from R to C, the transfer function from phi to Y, and the transfer function from phi to C, these are all stable. So now, let's close this loop. Let's put back delta, and let's derive the closed loop transfer function from R to Y. Okay, this is a pretty simple exercise. So So we have that y is equal to the contribution from r plus the contribution from phi. Except now that we've closed the loop, we also know that phi is equal to delta psi, and psi is equal to its contribution, the contribution from r, plus the contribution from phi. Oops. Yes. So now we can solve. So we put this back in here, and we get that phi is equal to delta TRC times R plus delta times this transfer function from phi to psi times phi. Now bring phi over to the left-hand side and solve. And we get that phi is equal to delta times the transfer function from R to psi divided by 1 minus delta times the transfer function from phi to psi times R. And now we plug this into here and find finally that y is equal to the transfer function from R to y plus the transfer function from phi to y times delta times the transfer function from R to psi divided by 1 minus the delta times the transfer function from phi to psi times R. So one thing we talked about is stability and what we called system norms. And we defined the norm, or the length, the generalized notion of length, or size, if you like, of a system to be the maximum amount that a system can stretch out a signal. So if I have some system G, I have an input and an output, one way to measure the norm, which is often denoted in this way, is the maximum. And remember that I have to write a supremum because these are signals and the maximum may not be attained, but wherever you see soup, you can really just think about it as being max, as the size of the input, as the size of the output divided by the size of the input. So this is, we normalize by the size of the input. This is really how much can the system stretch out the magnitude of the signal. Now, if we're measuring input size with, if this is equal to the integral of y squared, then this is a measure of energy. This is our typical measure of energy. So this concept makes sense. It's saying if I put in a signal of energy U, how much is the energy of the output? If this is unbounded, then the system is unstable. But if it's bounded, then the system is stable. And a key fact, which we're not going to discuss, is that if the system is stable, then its norm, defined in the above way, is also the supremum over all omega of G of I omega. Now, we don't have to worry about these details too much. The reason I'm explaining it is if we look back at this transfer function, let's copy it and bring it down. So this is the closed loop transfer function that we derived from R to Y. Oops. Let's move that over. We want this to be stable. So for it to be stable, we need, let's call this G, we need the supremum of G of I omega to be bounded. And let's note what this would be. If we plug in if so this is g omega, since we're assuming that all of these transfer functions to begin with are stable, since t r to y, t phi to y, t r to psi, t phi to psi, and delta, because delta is always assumed to be bounded in this way. Since these are all bounded, the only potential trouble can be caused by the term in the denominator, 1 minus delta times transfer function from phi to psi in the denominator. And this will be avoided if delta times transfer function from phi to psi, let me write this better, the transfer function from delta times the transfer function from phi to psi is always less than 1. And this is the condition for the small gain theorem. Another way to write this is that the transfer function from phi to psi is less than 1 over delta of I omega for all omega. So for example, if all we know is that delta of I omega is less than 2 for all of I omega, for all omega, then the condition for stability would accordingly be that the transfer function from phi to psi at I omega is less than 1/2. So let's see how we implement this in practice. Or let's so step 1 is to see what the uncertainty is. So if p true is equal to, say, p plus delta, then step 1 is to translate this into a block diagram. We did this above. This would be simple. This would be changing p into delta in a feed-forward parallel loop. Step 2 is erase delta and compute the transfer function from the input. So what's the input? Not the input of delta, so we've erased delta from the input to the output. This is the transfer function t from phi to psi, and then we finally just use it in the condition t phi to psi of I omega is less than 1 over delta of I omega. So if we go back to our feedback unity loop, this is step 1. Step 2 is to compute the transfer function from phi to psi. So let's do that. So psi is equal to k times whatever goes into k. And note that now I'm ignoring r. Okay, so I only want from, this is the usual thing when we're computing the transfer function from one input to one output, we ignore all other inputs. So psi is equal to k times whatever goes into it. What goes into k? Minus 1 times phi plus p times psi. I need to distribute this minus 1. So it's equal to minus, I got a little sloppy here, minus k, bring the minus 1 outside, phi plus p times psi. Or in other words, psi is equal to minus k phi minus k p c, or c is equal to minus k over 1 plus kp times phi. What's the small gain condition? So this is the transfer function from phi to c. What does small gain tell me? It tells me that t from phi to c should be less than 1 over delta, and this is exactly what we had before. K over 1 plus pk is less than 1 over delta. Or, if we want, we can rewrite this as in any of the ways we saw above. But this is just as we had above. So I would encourage you to do a few practice exercises. So for a practice exercise, just make up any block diagram. Perhaps doesn't have to be this complicated. H1, H2, H3, H4, and make up some, choose one of these to be uncertain. So for example, say H2 true is equal to something different than what we just did above. Maybe it's equal to H2 over 1 minus delta. And remember, step 1 is to draw the block diagram, representation of the uncertainty. And step 2 is compute the transfer function from phi to c when delta is erased. So I'll give you the answer here for the first step. We have H2. I want to turn H2 into H2 over 1 minus delta. So we can think about this as H2 times 1 over 1 minus delta. So I want to connect H2 in series to a block that will give me 1 over 1 minus delta. Whenever you see delta in the denominator, there must be some feedback of some kind. And you can check that connecting like this with no minus sign there gives me exactly what I want. So basically, I need to put this right above, right in H2, and then compute the transfer function. Here, let's actually do that. So we'll have this setup. And then step 2, which I won't do here, is computing the transfer function from input to output when we've ignored delta. And that is the small gain